It appears that we're live, and usual tests and such, just to make sure things aren't a terrible mess.
It appears that we're live, and
seems to be working. So the new microphone does seem to work here on this computer. So I'm, yeah, just overflowing in proper technology for a change. Anyway, found another program to do the camera thing in, and I can actually change the settings. So I have, for no good reason. And yeah, so enjoy it. Anyway, whatever. It serves no purpose, but I did it anyway. So I don't really want to do any drawing, but I do want to talk about some of what Feynman said about reflections. So I guess a simple drawing would suffice just to make a point. So you have a surface, should be a surface of some kind. And I'll make this line a little bigger so we can see it, and then we'll put arrows on it. And how we're changing the color, we'll just have to deal with one color. So we have this idea that if light comes in at an angle, it reflects at the same angle. More important, I would say, is that the likelihood that it reflects goes way up. So I could say at this kind of 45-degree kind of angle, you could have the expectation of maybe 50% of the light, is going to be reflected. Some lesser amount goes through at some other angle. Okay, not exactly the angle that went through. And yeah, that's the way it works. Something like that. And then you have these surface subjects. I guess I'll make the line a little smaller and take the arrow off. And there's the idea, okay, that this other surface also has the potential to create a reflection. So we'll, it'd be nice if we had a dotted arrow, but just have to, put a small arrow. That there could be a reflection from the bottom surface, and it would obviously be at a different angle because the light's coming in at a different angle. Now the question is, what is it reflecting off of? Is it reflecting off the bottom surface, or is it reflecting off the top of the next surface, right? I'm not certain, what exactly the truth is. So the idea would be is there's another surface here. And if these two surfaces are close enough together, you could understand that they would become bonded to each other in maybe not in an electrical way, if not in a material way. And that, so it could be that the light isn't reflecting off this second surface, it's reflecting off the top surface of the second substance. And so that's sort of a interesting question is, what is really causing the effect? Is it this other surface, or, this other substance, or is it this bottom surface? And so this gets to, where Feynman's talking in his lecture in Auckland a lot about light and reflections. And it comes up this whole thing because of lenses and mirrors, and then you get into interferometers. So it touches on a lot of subjects. So we really ought to have the facts really right. So in the Auckland conversations, so Feynman's talking about how much we can expect light to reflect off a glass surface. Now, the first argument I'd make is he's really talking about light that comes in perfectly straight. Because we know that if light's coming in at an angle, a lot of it's going to reflect, maybe half of it, maybe more. The tighter the angle, the more reflection you get. So this reflection number he's using, we shouldn't be fooled by it, because he's talking about photons we assume to be traveling exactly perpendicular to the surface. So I should be able to temporarily remove this. Oh, that still doesn't do it. Can't get to the color. Jeez. Just little subtle pains in the assy things like this could just make you crazy. Still can't get to the color. No, it'd just be nice if I didn't have to move everything into positions I don't want to move them in, just to get to the color to change it. Damn. All right, blue maybe. Oh, that's good enough. That's a nice color blue, I think. So this is in contrast to a conversation about what happens when light is just going straight down and then reflecting presumably straight back up. So this number, the percentage that we would expect, is 4%. Okay. So for glass. And the idea is that if you change the thickness of this glass, you carve little bits off of it, you change that number, and the number can go anywhere from 16% to 0%. So depending on how thick the glass is, it cycles through. So as you take off little layers, it goes 16, 15, 14, 13, 0, 1, 2, 3, 4, 5, back up to 16, back down to 0, back up to 16, back down to 0. And that gives you, under certain circumstances, obviously, where you're creating very gradual differences in thicknesses, that would give you a ringed pattern, an up and down, progressively light, progressively dark, progressively light, progressively dark. Newton's rings are the famous interferometer pattern. So I guess I should make some effort to draw that in some way or other. So we'll just see if they're not hollow circles. Okay. So I'd have to do it with different colors and start with a big color and then go smaller color and then big color and then smaller. Well, I'd have to do a lot of color changing. Well, ooh, that's kind of messy. We don't like that. Don't draw it there, please. Start here. Oh, it's no. Don't do that one either. So I guess we have to start here. All right. Whoops. I don't want to do that. Whatever that is. I didn't want to do that. I didn't tell you to do that. Unauthorized drawing by the program. So we'll put it here so it doesn't look too stupid. Maybe. Well, it's still going to look stupid because it's not exactly right. But anyway, so sorry for this, a little bit of a delay while I do this logistics of having to do this the hard way. Oh, yeah, this is really not going to work at all, Gary. All right, never mind. I'll give up and just move things around. And so you'll get the idea. So you go, Newton's rings it would just keep going red, blue, red, blue, red, blue, red, blue. I'll do one more blue one just to get the idea. And then I'll forget about ever trying that again. All right, so let's just make well, see, that circle's still moving. I don't want that to happen. Don't move this circle. No, stop that. Stop moving the circle. Oh, you got to turn the node thing off. Okay. Edit. Circle. Okay. Now I should be able to draw a circle. Okay, a little circle. And that's, ugh. No, I have to put the node tool on. Damn. I blew it, I think. Yep, I did blow it. Let's see if I can grab this one. Oh, look at that. I could make them ahead of time. Anyway, all right, so we're going to give up now because this is just a terrible waste of time. Forget that. Okay, go back to lines. Safer. Somehow my drawing paper is in the wrong position, so that's close enough. Yeah, you can see that, but when I put the other thing back, you won't see this anymore. But who cares? That's what I say. Who cares? I don't even know if there's no comments yet, so it doesn't matter. All right. Well, anyway, this was the only part that was important, was this stuff here anyway. Stuff you can see. All right. So what gets kind of complicated is just trying to figure out, see, if we could shoot light straight, then we could do all these precise experiments and we could get precise information, but we can only get this by generalizations. So when they say 4% reflects, aren't they really saying, isn't that 4% number completely dependent on whether the light truly is moving perpendicular to the surface? So any beam of light is obviously going to have elements of that light that isn't perpendicular. Even a laser beam has light that's not going perpendicular. It's veering. And those subtle changes presumably could have changed this reflective index. So that is, any angle is going to be more likely to reflect than perfectly up and down. So, I'm just thinking about it. I'm just saying, couldn't that in and of itself be an explanation for the variability in some bit of this number? Now, it doesn't explain why when you change the glass, that is, you polish it, that you change its reflective index and that you do so in a proportional manner. So that still has to be explained by acknowledging that you're changing something's arrangement. So I've speculated that, there's all kinds of ways you can stack things. So say if these were magnets and they had a positive and a negative side. It's not a very, they would line up with each other staggered, but they could also line up this way. So you could sort of understand they could have a negative pole, positive pole going this way off the magnet, or being staggered this way. And depending on how much of them were doing this versus this part sticking out would give you a change in the surface that could change the reflectivity. So that is as you polish it, you start removing these, and the surface becomes all of these. Okay, so it becomes a bunch of batteries going head, tail, head, tail, head, tail across the top, and the interior might be all batteries going up and down like this. But as you polish it, you start popping these to the surface, and the more that you pop to the surface as you're polishing, the more of these you end up with, the more reflective the surface. So it reflects off these and it is absorbed by these. So if a photon hits one of these, it goes through. If it hits one of these, it reflects. So you could sort of understand that as you're polishing, you would be making more of these. And that at some point, you make more of these. There's more of this, less of this. And that decides how reflective the surface is. Now, I haven't drawn up detailed diagrams of that kind of stuff, but you can sort of think it through if you just think about how you can line up magnets different ways and have them stick to each other. So you can just take regular bar magnets and, you can put them in different arrangements where they will be compatible, where you're sticking the right end to the right end, positive to negative, positive to negative. And you can make squares and different geometry in terms of how you arrange those magnets. And I would argue that that has something to do with the composition of glass and how the atoms line up. And it might explain why also glass is an insulator, because the fact is that having atoms going this way on the surface and atoms going this way on the interior, sort of logically you can say, yeah, that might not be very conducive to the transmission of electricity, where it might be conducive to the transmission of light. That light and just as electricity and magnetism are sort of perpendicular effects, that is, the magnetic effect is perpendicular to the motion of the electricity, that would sort of be intuitive that light might obey the same kind of rule. in terms of how it transmits. All right. So, yeah, so this really, to me, this is a really complex subject in the sense you got a lot going on here. So you have the fact that photons that hit a surface at an angle reflect more, regardless of what this 4% number is. It's going to be amplified substantially based on the angle the light hits the surface at. And then you have the thickness of the glass is also going to change how reflective it is. Now, the question would be, I don't think changing the thickness of the glass is going to change the fact that if I have light hitting this piece of glass at a 45-degree angle, I'm going to get pretty close to a 50-50 transmission versus reflection. I don't know what the actual number is, but it seems to me, just from my experiments, it seems close to 50-50. Maybe it's 39-60. Maybe it's something else, but I'm just saying, from what I've observed, it seems pretty close. So regardless of what it really is, it doesn't seem like the thickness of the glass changes that by as big a percentage as from 0 to 16%. So for light going straight in, the thickness of the glass changes from the glass reflecting 16% of the light versus reflecting 0%, which is a huge difference. And I'm just saying that I haven't observed, using different pieces of glass, that there was anything like a huge difference in that 50% number. Whatever the number is, it seems like whatever piece of glass I used, when I shoot the light at a 45-degree angle, I get pretty much the same amount of light going through as I get reflected. Now, maybe I'm just being lucky, and I've chosen pieces of glass that all have a similar, they're all of the same proportional thickness, of some number, 6% or whatever, and they're all within 2% of that, and so they all look the same, even though they're not. But it would be an interesting experiment to do. Clearly, this would, really help to have a whole bunch of pieces of glass, little thin pieces, and have your 0 piece and your, all very finely polished. Here's my 0 reflective index piece, and my 1%, my 2%, my 3%, all the way up to 16%. It'd be really nice to have those just sitting here to play with, to do these experiments. And that's something I haven't seen anywhere on the internet. It seems like some lab ought to do that and play around, do some experiments, with those precisely made pieces of glass, and see if you change the angle makes any difference, whether you get more reflection, more surface reflection based on the angle of the light changes based on the thickness of the glass. These are all questions that you sort of need to answer before you can sit there and fill in all the pieces of the puzzle. And that's sort of, like I said, is sort of the, what Feynman leaves off the table is really kind of important stuff that should be on the table, is the fact that we can't reliably shoot a photon at the surface of a piece of glass. We have little ability to aim photons. And that's a huge liability in doing any of these experiments, is the fact that we can't aim photons at all. Just can't do it. We have very little hope of predicting where a photon's going to go, one single photon. We can't launch one and say there's a 99.99% chance it's going to go to that exact spot. Just can't do it. And therefore it can't do any precise precision experiments to figure out any of this stuff. So these are just averages. So they send a bunch of light to the surface of glass and get 4% back, and they've drawn some sort of conclusion that all the light they sent down were somehow parallel to the surface, which they can't be sure it was, because even our laser beams can't do that. So, very open questions. And again, the reflection question of whether they have it right. So this is one they probably could do in space. I don't know if they've ever done it. Just to answer it, get over with, is, what does the light actually reflect off the bottom surface, or is it reflecting off whatever the other surface is? Air is a real thing. So it could be that when light's reflecting off the second surface of a piece of glass, that what it's really reflecting off is the top surface of the air layer. Okay, so it's always just reflecting off top surfaces. It doesn't reflect off bottom surfaces. Because you would almost argue that this could get very complicated if you count the bottom layer of the glass as one surface, and then the top layer of the air as another top surface. Then you have three surfaces. So now you'd expect to get a reflection off the top, another reflection off the bottom of the glass, and then another reflection off the top of the air. And is that how they calculate it or not? So that makes it a bit more complicated to figure out which one is engineering which. So the thing that is paradoxical is that if you put another layer of glass under a layer of glass, and it is of the right thickness, it can change the surface layer reflective index. So that's what makes that's what requires this to have some sort of quantum mechanical explanation, or some explanation that has to do with photons and electrons. Quantum electrodynamic explanation is clearly the second layer is communicating with the first layer. So the second, so if I take a piece of glass that has say an 8% reflective index, and I put another piece under it that, let's say, has let's see, 8 and 8 would be 16. Let's just say it has a 9%, right? And I put those two on top of each other, I can change this to 0. See, the 16 and the 8 plus the 9 would give you 17, and that would be recycled back to 0. So the 17 would be 0. So you would have passed the 16 layer, and now you're back to a 0 layer level again in terms of this thickness thing that keeps changing. So I mean, it's a subtle thing to understand. It changes for like 1 millimeter of glass. There would be like 10,000 cycles of 0 to 16. So you have to understand, just a tiny bit you're taking off, and you change the reflective index. So you're not like taking out big hunks, but big hunks could be taken out, and it'll do the same thing, because there's always going to be a proportional relationship to the volume, the thickness of what you're removing. So whole big hunks can also be added, even though the only thing that matters is the 10,000th of a millimeter part is the only part that matters. So anyway, so the point is when I put the second layer on, so you have one layer here and it's reflecting 8%, 8%, 8%, 8%, it's bouncing off. See, I keep doing it at an angle, and that's not the right way to say it. It has to be coming straight down, and 8% comes straight back up. And then I stick another piece under it, and all of a sudden this surface is doing 0 reflections now. It all goes straight through. How did this second layer tell this top layer, you're 0 now? And that requires there to be what I was talking about, some kind of communication. That is, all the electrons and the atoms of the glass are electrically connected. And so when something changes down here, it's basically forcing these magnets to rearrange their position. So something down here, the bottom layer looks like this. You put a new layer on it, and the new layer says, this one has to go up. And then this one says, I have to go down, or I have to go up. they have to readjust to what you put below them. So it's that readjustment goes back up to the surface, and the surface is changed to reflect the change that you added to the bottom surface, essentially, by pushing the two pieces of glass next to each other. Now, if you trap air between the two pieces, then this really gets complicated, and that's when you get all this Newton's ring stuff. That's when you start getting the internal reflections that create more effects that make this even more complicated. Yeah, so I'm not even going to try to draw all that because that gets more gnarly. So this video isn't intended to provide answers. It's just intended to say, well, if you have any sources that explain more detail about this reflection thing and how this works, fine. I'd be interested in any good detailed sources. That there are a list of questions that could be asked. What do we have for evidence demonstrating that the second layer reflection is a reflection off the bottom surface of the material and not the top surface of whatever the other thing is? See, if it's empty space, you can assume there can't be a second surface, right? I mean, so it would have to be off the bottom surface. But if there's no change, that is, if you can't get to that 16%, you could sort of surmise that the highest reflection rate you get on the top is 8, and you're getting 8 more from the bottom to get to that 16. So if you can never recreate a 16% reflective index with a piece of glass with a vacuum on the other side, then you sort of demonstrated that only the top surface is reflecting. So that experiment, I think, could be done. Now, whether it's ever been done and whether there's any way to search for it, unfortunately, there's probably no way to find it, to find enough specialized language to be able to find that specific experiment. But that would be one way of finding out, one way of deducing or collecting a good piece of evidence demonstrating that, yes, if you can't achieve that 16% number, that would indicate that the bottom layer isn't reflecting, or that the top layer of the other surface isn't reflecting, obviously, but that's not what we're talking about right now. And I guess it would depend on how much you can get out of that second surface, what its reflective index would be. So I don't know what the reflective index of air is. Two surfaces of air trapped between, I don't know how you can trap air between surfaces. I don't know how you could create air surfaces without creating some other material surface for the air to interact with. But yeah, it's an interesting, I wonder if the only way you can get to the 16% is by having 2 layers of glass on top of each other. And that if you don't have 2 layers of glass on top of each other, you can never get to the 16%. I'm not sure they ever do that 16% thing. That's a lot of reflection for light going straight through something. So that might be one way to tell. But anyway, it's a question that's open to me. So if somebody has knows of experimental evidence that truly demonstrates that the bottom layer actually does reflect and that it isn't the top layer of the next surface, I'd be interested. That's what I'm really looking for. And I'm looking for more data on how this experiment can even be conducted, in the sense of how you can ever shoot truly parallel light onto the surface, because that's really hard to do, right? I mean, how do you shoot light that isn't diverging at all? It's not coming from one source and spreading. How do you do that? How do you create those photons? Because frankly, if you can create those photons, then we could aim photons. And if we could aim photons, then we could aim them through the two slits and we could solve the whole mystery. So I don't even know how Newton arrived at these numbers with any reliability. How did Newton, I mean, just thinking about it, I mean, he's got to use sunlight. I don't even know how he measured the intensity of the light reflecting. Really curious. I mean, it is kind of a tough thing to do. And obviously, like I'm saying, is if the light is diverging from the beam at all, you're going to have more reflected light based on how much the light diverges. The more it diverges, the more likely the photon is to reflect, right? So the more I create a less than perfect perpendicular photon, the more the photon angles just a little bit, the more likely it is that photon will reflect, regardless of the reflective index of the glass. So maybe it's determining the reflective index of the glass. The glass wouldn't have any reflective index if you could truly shoot all perfectly parallel light. If you could shoot perfectly perpendicular light onto the surface of a piece of glass, maybe it would always be perfectly transparent. And just because we can't do that is why we can't get that result. I don't know, it's curious. To me, I find it interesting. Clearly, you people don't. So, okay, I get it. Well, I don't really get it, but I just have to accept it. So anyway, I'll just point out, I am interested in somebody who wishes to defend the conventional theories, wave theories, and probability built into the universe theories, and whatever, the standard quantum mechanic answer, which is, yes, there's probabilities that are being caused by not the physics of the materials. The materials aren't causing this effect. Somehow the photons have it built into them, and they're the ones deciding. And I'd really like to have that conversation and explore whatever evidences you have that convinces you that this theory of waves, which I don't think explains anything, are raw, indeterministic probability mumbo jumbo, is how to answer these questions, and that these questions don't have anything to do with what glass is and how glass atoms are arranged. And that's what's deciding exactly how these things reflect. So the other thing I wanted to point out, but I remembered something else, was the idea that when you think about the surface having an irregularity to it, and I think I'll just try to draw it for the sake of not taking too much time. So you can understand that if it was magnets, let's say, lined up with each other, that the magnets, okay, would have a body to them, okay, and the bodies of the magnets are lining staggered, okay, so the plus end of one magnet is lining up with the negative end of the other magnet, and so it creates this uneven surface. And you could imagine that that provides an opportunity for the reflection idea, so that if light did come in at an angle, that it would bounce off these surfaces, in very specific ways that could, okay, duplicate angle in, angle out. So you can sort of understand that, yeah, that does work. I mean, it's not an unreasonable way to think about it, is that it comes in, does this equal bouncing off each surface, and will leave at exactly the opposite angle. So whatever angle it comes in at, it would leave this interaction with this square going out exactly how it came in. it would create the proper reflection. Now the same is argued for inside of that what creates rainbows, except rainbows are inside circles. So you can understand this is more of an obviously the geometry I'm talking about here is kind of very square, obviously. But and I'm saying that atoms can probably have that kind of geometry. That's what magnets do. Magnets can create hexagons and octagons and shapes like that in terms of balance pressure between them. And rainbows, the idea is it's a circle, and you have 2 or 3 reflections. Decides where. That's why you have a double rainbow, is that if it reflects a 3rd time, it makes the second rainbow. If it only reflects twice, it makes the regular rainbow. But the light comes in, makes 2 reflections, and creates the rainbow, or 3 reflections. So it's 3 reflections, and the 4th reflection makes the second rainbow, right? So, well, it's something like that. Light comes in this angle, bounces off this surface, reflects over here. If it reflects a 3rd time, I would send it down this way. So that'd be the wrong place for the rainbow. Well, anyway, it's something like that. I don't remember the exact geometry. But the idea, the light comes in at an angle, and it's bouncing inside the bubble of water, the sphere. Which is interesting. I mean, it's obviously not hitting water molecules. It's not hitting the water bubble. And it's refracting as it goes through the bubble. So I guess that's part of what changes the angle. But it's always, there's lots of rules about this 43 degrees or something. The light has to come in at 43 degrees and blah, blah, blah. So there are rules to the geometry. I just don't remember them. So anyway, there are ways to look at this. Like I said, the mechanics, the irritating thing I'm saying is with physics is they're not even paying any attention at all to any kind of geometric explanation. Well, it's over here. Any kind of idea that you could, talk about the geometry of the substance and talk about what the photon is doing in the geometry of the substance. Now, they do that with rainbows. Okay, but they don't do it with a piece of glass or a mirror or all of these other examples like the interferometer. There's just nobody pays any attention to the travel of the photon and what it's interacting with, whether it's interacting with a piece of silver or whether it's going in between 2 pieces of silver in single slit. No one's paying any attention. And to me, that's where the physics is. That's why there's an effect being caused by the material the photon is interacting with. And I mean, this whole conversation is taking place as if these materials mean nothing. Feynman talks about the surface as if it's a surface, and it just doesn't have any. It has no geometry. It has no structure. It's irrelevant to the conversation. And clearly it's relevant. And the real answer is in there. And all these people have just given up on doing any exploring, looking for the material reaction. I mean, the material action that's taking place, and recognizing that these are complex substances that the frickin' photon is interacting with. It's not interacting with nothing. It's interacting with a substantial something. And it's not even a conversation anywhere. That's just wrong. So, yeah, I could play the other Feynman, video where he's going into the, Newton's glass, the layered glass. And I have played the video before, and it's an interesting conversation. The only bad news is that's one of the videos the sound quality is pretty bad because he had to switch microphones and blah, blah, blah. I mean, it's not that bad. But yeah, there's just not enough in it. There's not enough truth value in the sense that, like I said, he doesn't really talk about how, this glass argument about it having a reflective index, that reflective index only has to do with photons moving one way, perpendicular. Photons moving at angles aren't going to obey any 4% rule or 8% rule. They're going to obey a different rule. Very different. So this gets a little more, it's more complicated than what he's conceding. And it's certainly, we don't have any, he keeps talking like we have this precision. Like I said, even in the previous video, I played the part where he's talking about how, well, we know there can't be spots in the glass because we can shoot a photon right on that spot and see if it goes through each time. We can't do that. We can't test that theory. We can't prove that isn't true. He's just assuming that's what the results would be. You can't do the experiment. That's it. Not very good at physics. That's all I'm saying. Not very good. Ain't right. Okay. So I'll give you a couple of minutes if anybody's got anything at all to say. It's it's a very tough racket doing these talk physics. That apparently nobody wishes to talk physics. Talk about physics. All they want to do is math equations. They don't want to talk about underlying theory and whether it's right or wrong or any of that stuff. No, not interesting. It's amazing. We've all bought into we believe the Pope. Pope is the guy who knows. I'm not going to bother reading the Bible or paying any attention. I'll just believe whatever the Pope says. I'm a good, faithful sheeple. I guess that's how people want their physics. I'll just trust them. Even though what they're saying can be demonstrated to be kind of loose and sloppy, like somehow we've done the experiment they haven't done. We put detectors on, and when their detectors were on, the pattern changed. It never happened. This experiment is theoretically impossible. You can't detect a photon. It's a silly prospect. It can't be even done. No rational physicist would even try to detect a photon in its travel because he knows he can't do it. Can't bounce anything off of a photon without, so it's like bouncing, it's like throwing baseballs at moving ping pong balls. So you're not going to be able to see the ping pong ball. The baseball is just going to wipe it out. That's the end of the ping pong ball. You're not going to see that one again. No. It would be like trying to videotape humans by shooting x-rays at them, high intensity x-rays and bouncing them off and just, but you melt the human, right? And be like, oh yeah, I can't see him because he melted. Can't do it. And such. Room 5? I mean, no comments. Nothing. Absolutely nothing. Amazing. It's not exactly amazing, but it's just disturbing. 7 viewers. It's pretty bad. All right. Well, okay then. Yeah, I just wanted to bring the subject up. It's just going to take time. That's the problem, right? I mean, I could spend a few days working on it, and then present some sort of stuff. But what I've concluded. But yeah, the real trick is some of these questions have probably already been answered. So why should I redo what somebody else has already done well? So this is just one of those times when it's just kind of irritating. There isn't there isn't better feedback. That's okay. It's clearly something I'm stuck with doing because nobody else has done it. It's like I said, there's no real good video that goes through the process of what an interferometer does, how the photon travels through the device. And it's just kind of tragic that that doesn't exist in an atmosphere where people are so arrogant that they know it's wave interference. You know, they know it, even though there's not one piece of good evidence that they have reason to think they know it, besides somebody saying it. So. It is 60 more seconds. Call it a day-ish. Just one more last look at the drawing paradox problem. How do you tell the difference between the reflective index and the fact that as you increase the angle of reflection, you increase the likelihood of reflection? There's got to be a relationship between those two things somewhere. Somebody's got to tie that together. Yeah. Alrighty then. Till the next time and such. So forth and whatnot. Yeah. Oh, the other thing I wanted to know is somebody who can tell, because there's, it's not really easy to tell. There's no way to test the channels. I mean, yes, there are ways. They're just a pain in the ass. So I was just wondering if somebody can overtly know right away just by saying, yes, my computer does that right away. I can hear the difference. Do you hear a difference, like especially in the last video, between the two stereo channels? I mean, you should have heard Feynman through one of the channels better and me through one of the channels better. I mean, I should be louder in one channel and whatever I'm playing should be louder in the other channel. I mean, I guess I could tap on the channels and then you could tell me, when can you hear this in one channel and can you hear this in the other channel? Somewhere else. One way or the other. One of us is going to have to keep wasting my life with this damn button. Stop it. It really was good. It's been, I had a bunch of trouble, and it's been great for like 3 or 4 weeks. It started up again. Anyway, I have to start sticking screwdrivers in there. Anyway, till next time.